Hey everybody, I've been waiting a while to show you this problem. This problem was posted on the SyberMath website, and it's a little bit different. It's a floor function, but it's the left-hand side is not actually. The right-hand side is just the function itself. I'm on the screen here for you guys. Let's see. There we go. That's a little bit better. All right. Now, a lot of the floor functions that we see is floor of some function equals a floor of some other function. In this case, we just have the floor of 3 minus 2x equals to the function x squared minus 3x. Everybody knows the sketches of these graphs. This is a graph that's, the graph of this line is always decreasing. And this is a parabola with intercepts, 0 and 3, x-intercept 0, 3. And also it would have a vertex of 3/2, that's halfway between 0 and 3. And so you already get a mental picture of approximately where these solutions may occur. And you can't get away from that. The parabola decreases from minus infinity to 3/2, and then it starts to increase the vertex, from 3/2 to infinity. But again, the key is that gives you some insight, but you need to be able to work it without an over dependency on the graph, in my opinion, at least. Now, the approach that I'm endorsing here is there's very little algebra going on, but the arithmetic is tedious. And the only two things you really need to know about the floor function is that the floor of any expression goes to an integer, period. All right, any expression, all number, algebraic expression, maps to z, the integers. And also, the floor of an integer is an integer. And that's really just a property of what they call the greatest integer function. Now, it helps to see if find out where the two graphs would intersect, or just set the two expressions equal to each other. And when you do that, you get that the graphs intersect at 1 plus root 13 over 2, which is approximately 5/2. That's the closest rational number approximation. And 1 minus root 13 over 2, which is approximately minus 3/2. And I just used the approximation square root of 16 is 4, and you get a decent, you get something that's kind of close, a ballpark figure. And so already you expect to be looking for solutions that are near these numbers, because again, the squaring function grows pretty fast, and it's just going to take off and run away from the linear function. So it makes sense that the answers would be somewhere in neighborhoods of 5/2 and minus 3/2. Now also what I've done here, just to keep myself organized, this row right here really means floor changes. And right here, this is just the values of the function. Now, that's obvious if you look up here. There's no floor function over here, but there is a floor function over here. But I had to keep this straight by just writing it down. Otherwise, my thought process got kind of cobbled, But what you'll notice here, when I call it a floor change, it's really just a floor value, but it maps to an integer, right? Minus 4, minus 1, minus 2, 3, 2, and 0. Those all, the floor of this function has to map to an integer. Now the value of the function itself just goes to whatever it goes to. Now I was just kind of spitballing and putting numbers in there to see what was close, but you'll notice 2 is where you have a floor change. When you put 2 in over here, you get -1, and the floor of -1 is of course -1. But notice here, when you put 2 into the function, you also get -2. So they're not far away. The floor value of -1 and the functional value of -2. All right, again, the floor value. So you're thinking, that may be a good place to start. And also at 5/2, there's not a whole lot of distance between the floor value and the functional value. In fact, there's a distance here of 3/4. -2 to -5/4 is 3/4. So that's why I decided to start somewhere near those numbers, 2 and 5/2. Now let's move down here just a little bit and see what I got for you here. Now, yellow, I left out some of the details of some of the calculations, but the floor of 3 minus 2x is equal to -1 on this open closed interval. Now let's just check. If you put 3/2 directly in here, you would get 0, right? 3, if you substitute 3/2 in for x, this would actually give you 0. So that means you have to make this an open interval. It's anything beyond 3/2, which will produce a floor value of 1. And also the very last floor value of 1 will happen when it's equal to 2 closed. So you see 3 minus 4 is -1. So we do know that the floor of 3 minus 2x is equal to -1 on this interval, all right? Now, but we also have to check the functional value. See, we're talking floor value -1 on this interval. If you set this function x squared minus 3x equals to -1. Now, again, I didn't write down all the quadratic, that just clutters it up, but you guys can see that what you would get right here is you would get x is equal to, I think, 3 plus √5 over 2, all right? And you would also get x is equal to 3 minus √5 over 2. Well, it's pretty easy to determine without, no calculators here. 3 plus √5 is approximately 7, right? So, and then 7 over 2 is definitely not in this set. All right, now just think, and then 3 minus √5 is a number between 0 and 1. So again, even though we have a floor equals to -1 in an area you think they may intersect, they really don't. So there's no solutions in this interval right here from 3/2. So we know that there's no solutions in a suspected neighborhood here. Okay, now let's keep going. Now this next one was really kind of amazing. And this one cost me 2 hours and about 2 hours of sleep too. Now, we've got to be very careful right here. So we've taken care of -1. We know there's no solutions in the interval related to -1. All right, now let's try out the floor value of -2. Now, this is where, gosh, this killed me. It really, thought I was just going to pass out. I thought I was going to have to give up on the problem. But if you put 2 in right here, all right, you would get -1 as a floor, right? We've already seen that. So you have to leave 2 out of here, right? Again, folks, if you substituted 2 in right here, you would get -1 as a floor. But if you go beyond 2, you're going to get floors of -2. Check it out. If you do 5/2, you actually get a floor of -2. If you put 5/2 right here, you get 3 minus 5 equals -2. All right, so there's no doubt that this is a parentheses here, right? It's an exclude. We do have to exclude the 2. But here's where I thought I was going to have a nervous breakdown right here. It turns out that 2 is a solution to this equation. Now, it actually factors if you want to factor it, but by inspection, you can see that 2 is a solution to this equation. When you set the function equal to -2, you put a 2 there, you get 4 minus 6 equals -2, right? So 2 is a solution, but that's too bad. 2 is not a member of this set, right? See, this guy was excited too. He goes, what? I double and triple checked it, but that's about as close as you can get, right, guys? So in other words, 2 is a solution to this equation, but it's not contained in this interval by the narrowest of margins, okay? So I hope you guys like this notation. I kind of like it. They call it a negated relation. 2 is not a member of this set, which is what we're interested in, but it is a solution to this equation. So that's terse, but I think it gets the point across. All right. So now we know that there's no solutions in the intervals 3/2 to 2 and 2 to 5/2. All right. Now let's move along and deal with some negative numbers here, folks. Now I won't run through all the spitballing I had to do here, but I found out that you were as close as you were going to be at the floors of 4 or 5. All right. Now, again, in a similar fashion, and again, I won't go through every last bit of it. It's getting kind of nauseating, but there's no solutions in this interval, but -1 in the same sort of way just almost worked. And you guys can verify that. Okay, -1 just about worked, but it was just right on the margin of the open-closed interval, Now, so then I tried it at 5, all right, which if you substitute various numbers in, you can try. I thought about trying it at 6, but when I tried it at 5, we had a miracle here, folks. The floor of 3 minus 2x is equal to 5 in this interval. And again, you can verify that by just substituting the numbers in, all right? And so you can, now we got to check the function again. If you set x squared minus 3x equal to 5, this is your solution. This is your solution. And right down here, I've verified for you that it's actually contained in this interval. Now, this is almost like an intermediate algebra problem all by itself. This blue solution, proposed solution, is bounded below by -3/2 and above by -1. All right. And it follows from the fact that 5 is less than root 29 is less than 6. Again, that's something that was done without calculators. This thing took me like 7 or 8 hours, you know. So we have a single solution. Now, I could get a little bit more formal and say there's no way we're going to have any more solutions, but I'm not going to do that. I've already spent enough of your time. But basically, the approach here, there was only one solution to this equation, the intervals where there was a chance. And of course, that was based on knowing approximately what the graph looked like and knowing that the x squared function is going to outgrow the linear function to where there's no way the floor function is going to catch it. So anyway, this is the only solution, folks. 3 minus root 29/2. Again, I don't champion my approach as the best way, but it's kind of a way to exhaustively get to the answers without really having to know too many of the floor function properties or do too many algebraic manipulations. All right, hope y'all enjoyed that.